Hello and welcome to the Chemistry Solution. This tutorial covers electron configurations, including Hund's rule and the Pauli exclusion principle. First, let's talk about orbitals, shells, and subshells. Quantum mechanics describes the probability of finding an electron in space using wave functions. And unless you end up taking physical chemistry in college, you really don't need to know much more about this process. But the quantum mechanical model uses three numbers to describe an orbital. The first is n, and n is equal to the energy level, or shell, and it's in these energy levels that the subshells and orbitals reside. Now the energy level has an integer value starting with 1. The second quantum number is L, and that's equal to the shape or subshell of an orbital. And so L can have any value from 0 to n minus 1. And the shapes of orbitals are denoted S, P, D, and F, and we'll talk about those more in just a minute. M sub L is equal to the orientation in space of an orbital. And so the value for M sub L ranges from negative L all the way to positive L. Now I said that the shapes we refer to are S, P, D, and F. S subshells have only one orientation in space. P subshells have 3 orientations, D subshells have 5, and F subshells have 7 orientations in space. Now each orbital can hold 2 electrons with opposite spins, and we denote these as plus 1/2 or minus 1/2, and this is used as the 4th quantum number to describe an electron. Now, this might seem very confusing, so let me recap now that I've kind of told you what all these numbers are. First, you have the shells, and these are the energy levels. Inside each shell, you have subshells, and these subshells have different shapes, S, P, D, and F. Inside each subshell, you have orbitals, and each orbital can hold 2 electrons. So because the S subshell has only one orientation, that means there is one orbital in the S subshell, and that orbital can hold 2 electrons. Because the P subshell has 3 orientations in space, that means in the P subshell there are 3 different orbitals, and each one of those 3 orbitals can hold 2 electrons, giving the P subshell the capacity to hold 6 electrons. And likewise, the D subshell has 5 different orientations, which means there are 5 D orbitals, and each of those orbitals can hold 2 electrons for a total of 10. And each F subshell has 7 orientations, meaning it holds 7 orbitals or 14 electrons. This will become a little more clear as we start diagramming our electron configurations. Let's start by drawing out the electron configurations for the first 6 elements on the periodic table. Hydrogen has 1 electron, helium 2, lithium 3, beryllium 4, boron 5, and carbon 6 electrons. So for hydrogen, we need to diagram 1 electron. You always start with the 1s subshell. 1 denotes the energy level, and S denotes the subshell. So we'll draw the electron like a half arrow. Now let's look at the electron configuration for helium. We need to diagram 2 electrons. Remember that each orbital can hold 2 electrons. So we draw in the first electron, and then whenever you're going to pair up electrons in orbitals, they need to have opposite spins. So we diagram the second electron as an upside down half arrow, and this denotes that the 2 electrons have opposite spins. And what the Pauli exclusion principle states is that no 2 electrons in the same orbital can have the same spin, or no 2 electrons can have the same 4 quantum numbers. So if you go back to that previous slide, you'll see that the 4th quantum number was denoted by the spin of the electron, M sub S, as either plus 1/2 or minus 1/2. So in any given orbital, your electrons need to have different spins. Let's draw the electron configuration for lithium. We'll again start with the 1s subshell. It can hold 2 electrons. We always place electrons in the lowest energy orbitals first. so you always place electrons in the 1s orbital first. If you go back to the previous slide, you'll notice that the value for the subshell, or L, the shape of the subshell, has a value from 0 to n-1. And so the energy level 1 can only hold the S subshell. Now that that subshell is filled, we need to go up an energy level to the 2s subshell. And we have one more electron for lithium, so we place that in the 2s subshell. Now let's draw the electron configuration for beryllium. Again, we start with the 1s subshell, putting in electrons with opposite spins, and continue to the 2s subshell. First placing our third electron, and just like we did with the 1s subshell, placing our fourth electron in the 2s orbital with an opposite spin. Moving to boron, we place our first two electrons in the 1s subshell, then we place our second two electrons in the 2s subshell. But for the n=2 shell, you have not only the s subshell, but you also have the p subshell. So remember that the p subshell contains 3 orbitals, each with a different orientation in space. And so our fifth electron goes into one of the unoccupied 2p orbitals. Now let's draw the electron configuration for carbon. We start with the 1s, placing our 2 electrons with opposite spins, then the 2s, again electrons with opposite spins, and then the 2p. We place our first electron in one of the unoccupied 2p orbitals, and when we go to place the 6th electron, instead of immediately pairing it up, we place it in one of the unoccupied 2p orbitals. So Hund's rule says that for orbitals of the same energy, or degenerate orbitals, electrons with the same spin will singly occupy each orbital before pairing up. So as I was drawing my electron configurations here, I was going from lowest to highest energy. The 1s orbital having the lowest energy, followed by the 2s orbital, followed by the 2p orbitals, which are all equal in energy, or degenerate orbitals. That means that as I place my electrons in the 2p orbital, I maintain the same spin and put one electron in each orbital before pairing them up. We can then write our electron configurations in an abbreviated fashion by writing the energy level and subshell, followed by the number of electrons in that subshell as a superscript. So for hydrogen, we would write that 1s1. Helium would be 1s2. Lithium would be 1s2, 2s1. Beryllium would be 1s2, 2s2. Boron would be 1s2, 2s2, 2p1. And carbon would be 1s2, 2s2, 2p2. Now you might be wondering how to keep track of what order in which to fill these orbitals. Here's a simple diagram you could make, remembering that the n=1 shell contains only an s subshell, while the n=2 shell contains only s and p subshells, and then the n=3 subshell contains only s, p, and d subshells. And then finally, when you get to the n=4 shell, it contains S, P, D, and F subshells. So you can draw this diagram just like this, and then draw diagonal lines through, which will tell you the order in which to fill these orbitals. First you fill the 1s orbital, then the 2s, then the 2p orbital, and then the 3s. And this next step is where it gets a little bit confusing. After you fill the 3s orbital, you fill the 3p orbital. But before you fill the 3d orbital, you actually fill the 4s orbital first. And that's because even though 4 is a higher energy level, the 4s orbital actually has a lower energy than the 3d orbitals do. So you fill 3p and then 4s, followed by 3d, then 4p, then 5s, etc., etc., etc. And so this is a great diagram to help you keep track of which order to fill the orbitals in, because it does get a little confusing. Let's look at a more complicated example. Let's write out the electron configuration for the element argon. Now remember that a neutral argon atom has 18 protons by looking at the atomic number on the periodic table. And if it's a neutral atom, that must also mean it has the same number of electrons, or 18 electrons. We then need to diagram these 18 electrons into the proper configuration. We start with the 1s orbital and place 1, 2 electrons with opposite spins. The next orbital we fill is the 2s orbital, where we place 1, 2 more electrons with opposite spins, so now we've placed 4 electrons. The next orbitals we fill are the 2p orbitals, placing 1 electron singly in each orbital before pairing them up. So there's our 5th, 6th, 7th electrons, followed by the 8th, 9th, 10th electrons. After we fill the 2p orbital, we fill the 3s orbital. And here are our 11th and 12th electrons. After we fill the 3s orbital, we fill the 3p orbitals. And here are our 13th, 14th, 15th, 16th, 17th, and 18th electrons. So now that I've diagrammed all 18 electrons, I know that this is the electron configuration for argon. And if I were to abbreviate it, it would be 1s2, 2s2, 2p6, 3s2, 3p6. Now what's interesting about the noble gases is that they have completely filled shells, and so we often use them to abbreviate the electron configurations of other elements. So if we were to write the electron configuration for vanadium, vanadium has 23 electrons. I'm going to write this electron configuration directly in the abbreviated method. So in the 1s orbital I place 2 electrons, so 1s2, then 2s2, so that's 4 electrons, followed by the 2p orbitals, which can hold 6 total electrons, so now I've placed 10 electrons, followed by 3s2, there's 12 electrons, and 3p6, there's 18 electrons, and then the 4s2 orbital, that's 20 electrons, and the last 3 electrons go into the 3d orbital, so I have 3d3. This electron configuration contains all 23 electrons and follows the diagram that I showed you before for remembering which order to fill the orbitals in. From the previous slide, I've drawn our electron configuration for argon. So you can see that the electron configuration for argon is exactly the same as the first part of the electron configuration for vanadium. So oftentimes we write electron configurations abbreviating the inner shell electrons with the noble gas configuration. So I would write the electron configuration for vanadium as an argon core followed by 4s2 3d3. Thank you for watching the chemistry solution. We hope you enjoyed this tutorial.